Hello, class. We will continue the recorded lectures on section 7.3, the central limit theorem, and now do some calculations using the central limit. So the idea again is that given enough samples, and according to the statisticians of the world, more than 30, that the mean of any distribution approximates a normal distribution. And so to review of just the what I would call general definition is right here. And so the idea is that mean will approximate the mean of the population for that particular experiment. And the standard deviation will be the population standard deviation divided by the square root of the number of samples. And so let's just walk through an example or two and show you how to do these calculations. So again, because it approximates a normal distribution, the good news is we use the same normal distribution functionality that we did in the last two sections. So this one says US census that the mean age of a college student is 25. With the standard deviation at 9.5, which is pretty big, right? And so if you randomly sample 125 students, what is the probability that that group has a mean age of greater than 26? So what is our strategy? Well, here's our strategy. Let me pull up the whiteboard here. And I don't think I hit the right buttons. Let me try again. Here we go. And so, as we said, the mean is 125, and the population standard deviation is 9.5. So what happens here if n is 125? And we want to calculate the probability that the mean of this sample is greater than 26 years. So when we do the normal distribution calculation, we need two things, right? Well, we know that the sample mean, x bar equals mu, and that would be 25. And the population, the sample standard deviation would be the standard deviation divided by the square root of n. So when you do that calculation, you would get 9.5 divided by 125. And if you did that, it would get 0.85. So then the next thing you need to do is to go back to our normal distribution calculation. And remember, when you do greater than, it's the same as 1 minus the probability of x being less than 26. So when we do this calculation, I'm going to show you on the spreadsheet, or you could use the norm CDF in your calculator, one or the other. And so, again, I clicked the wrong button. Let me try again. There's the spreadsheet. So we're going to do, this is 1 minus the probability of x being less than 26, right? And so to do that calculation, it would be equals 1, and then minus the norm.dist. So more functions, norm.dist. So here we would have 26. Here we would have a mean of 25. Here we have our standard deviation, which is what we just calculated, 0.85. And here we would have true. And so the idea of the mean being greater than 26, right, is 1 minus less than 26 is almost 12%, right, 11.97%. And so, again, the wrong button. I'm having trouble with buttons in this recorded lecture. There's the right button. And you can see you get 11.97 or 0.1197. calculation. So again, the same style of calculations, except you got to be careful on what your new standard deviation is in here. So let's do a couple more. So what does this say? Cattle are one of the most popular breeds. Hereford cattle, based on the data, the mean weight of a 1-year-old Hereford bull is 1,135 pounds with the standard deviation of 97. So would it be unusual for the mean weight of 100 head of cattle to be less than 1,100 pounds? And so remember, this crazy term they use is unusual is unlikely, which would be less than or equal to 5%. And so we're looking for this probability of less than or equal to 5%. And so again, we have n equals 100. And so our mean is the mean, which is 1135. And our standard deviation will be 97 divided by square root of 100, which is 10. And so that would be 9.7. So when you want to do this probability, we want 1135 for the mean and 9.7 for the standard deviation. And the idea is it's going to be less than 1,100 pounds. So if we go back to our spreadsheet here, this would be, let me make this a little bit bigger. There we go. So this would be the probability of X being less than 1,100. That's not less than, let me try that again. There we go. 1,100 pounds. And so now we don't have to do 1 minus, right? Because it always gives you less than. So it'd be equals, and then norm.dist, it'll be the one we use the most. And so here's 1,100. And the mean was 1135. Standard deviation was 9.7. And again, always true for continuous distributions. And you can see that that number becomes really quite small with regards to that. Let's see what kind of numbers here that decimal points. I need some more decimal points. Here we go. There we go. So you could see I had that formatted. I must have did another calculation, but you could see it's really, really small. So that's definitely less than 5%. That's less than 1%. And so you would say that this would be an unusual event that if you randomly take 100 these cattle and you weighed them all and calculated the mean, it's not going to be less than 1,100 pounds. And you can see that they got a really small number as well, and it looks like that matches. So let me do one more here, and this one I took out of a different book that I used, but this is a good calculation as well. And then what I'll do is I'll jump on to Alex and do one of the homeworks for you. So this one says, in a recent study, the mean age of a tablet user is 34 years. So that would be 34. And suppose the standard deviation is 15. And then if we have a sample size of 100, question 1, what is the mean and sample using the central limit theorem idea? So let's do that on the whiteboard again. See if I can click the right buttons this time. There we go. So when we take a look at this, we have a mean of 34. And remember, the mean also equals the mean. So that would be 34. So our standard deviation here is 15, but our standard deviation using the central limit theorem is square root of n. In this case, n is 100. So when you do that, you would get 15 divided by square root of 100, which is 10. And so that would be 1.5. And so the next question is find the probability that the sample mean is more than 30 years. So the probability that the sample mean is greater than 30. And so that would be 1 minus the probability sample mean being less than 30. And so this would be binomial.dist. And so that would be 30 for the point, 34 for the mean, 1.5 for the standard deviation, and then true for the cumulative. So let me do that calculation for you here on the spreadsheet. Oops. Try again. This would be 1 minus the probability of x plus 30. And so this would be equals 1 minus, bring up norm.dist. And this would be 30, be 34, standard deviation of 1.5, and then this would be true. You can see it's a really small number again. And so when you subtract it from 1, you're going to get a really big number close to 1. But let me format these cells. It looks like I formatted them for no decimal points. So let's get a few decimal points here. So you could see that the probability of it being greater than 30 is really high, right? Over 99%. And so with regards to that question is that if you had 100 people, that there's over a 99% probability that the average age of those 100 people is greater than 30. So do you remember how to do this idea of percentile? Well, just to remind you, when we do the percentile, we use the norm.inv. And the idea is that it'll give you that 95th percentile. And again, remember, this is the sample mean for the 100 people that we're sampling. And so when you do that calculation, it's norm.inv, and then 95, and put it in decimal, 0.95, and then the mean and standard deviation. So again, let me just show you that. This is the 95th percentile. And that would be norm.inv. And again, 0.95. Mean is 34. And this one is 1.5. And so when we do that, the 95th percentile of that mean of those 100 people is about 36 and a half, right? And so that's what that point means with regards to that. So I think it would be nice to take a look at one of your Alex homework. So what I will do here is, if you'll just bear with me a sec, I thought I had it up. It doesn't look like I do. Somehow it went away. Oh, here it is, found it. So let's do this problem here. So this is problem 4. And so what problem 4 states? That the sample size of 6 is drawn from a normal population. And so because it's normal, the number of samples don't matter because it's a normal distribution. Any other distribution has to be greater than 30. And so when you do this calculation, we have a mean of 61 and a standard deviation of 14. And you can see it says use your fancy calculator. You could also use the spreadsheet as well. And so question 1 is yes. because it's a normal distribution to begin with. And question 2 says find the probabilities between 51 and 71. And so our n is really small, which is just 6. So let me set this up on the whiteboard here first for you. So again, we have mu of 61, and since it's a normal distribution, that would also be the mean. Standard deviation of 14, and n equals 6. And because it's a normal distribution, we could still use the central limit theorem, and that would be backwards. It would be 14 on the top. Whoops. Put the blue back up there. Man. You hit one wrong button and you can't get back to where you want to go. Here we go. 14 divided by square root of 6. You get out your calculator 14, 6 square root. And so that looks like that would be 2.45 if we round to 2 decimal points. If you keep going, it'd be 2.44949 for a lot more decimal points. And so the question is, find the probability of sorry, I'm just writing this down. Find the probability between 51 and 71. So that would be the probability of the mean being less than 71 minus the probability of the mean being less than 51. And you would think that's going to be pretty big. That's a range of 20, and 61 is the mean. So it feels like it's right there in the middle. But we only have a standard deviation of 14, right? And then 6 square root divide. Whoops, I did this wrong. Glad I double checked because that number didn't look right. So let's start over here in the standard deviation calculation. So it's 14 divided by square root of 6. I must have divided by 6 instead. So let me do that again. 14, and then 6 square root is, oh, that's 2.449. I forgot to hit divide. So when you divide, you get the standard deviation of 5.7155. And so you still think this is going to be pretty big because that range is big. So let's do that calculation. So if we go back to the spreadsheet. Okay, I have to write one more number down because when I leave it here, I lose all these numbers on my whiteboard. So 7155. Okay. So going back to the spreadsheet, we're going to do probability of x being less than 71 minus the probability of x being less than 51. And so when you do that, we could just do it in one cell and just do the subtraction, more functions. So that would be norm.dist in this case. And so the first one is 71, 74. The mean is 61. Our standard deviation is 5.7155. And then we'd have true. So you can see 95% is from 71 down. So now what we want to do is to go back up here and subtract the 51. And so when you do that, you do the exact same thing, except instead of x being 71, it would be 51. was it 5.7155? And that would be 2. And so you see when you subtract the 2, it's almost 92%. So a big percentage, even with a sample of 6, because we're starting with a normal distribution. And so the last problem states the percentile. So the 81st percentile is going to be the norm.inv. So the 81st percentile is more functions, norm.inv. And so that would be 0.18 per 81. Mean is 61. And this would be 5.7155. When you do that calculation, it would be just over 66 pounds. So the 81st percentile for this mean of that small sample is 66 pounds. So that ends our recorded lectures for section 7.3, which is the central limit theorem on samples approximating normal distributions of the mean.